You are watching session number 1 of the chapter Chemical Reactions and Equations. In this session, I am going to discuss about the concepts like physical change, chemical change, chemical equations, and finally balancing of chemical equations. So let me start with the first concept, physical change. Opposite of physical change is chemical change, and try to know changes around us can be classified into two different types. We have a n number of classifications. The one type is physical change and chemical change, the changes around us what we see. So first we will see what actually the physical change stands for, and some examples I am going to discuss, and later I am going to talk about the chemical change and the examples for that one. Remember, one simple example I will consider, that is melting of ice. So this is a process, and what happened here, ice was actually in the solid form, and melting is nothing but we are supposed to pass heat, then ice is going to be converted into liquid water. So instead of saying the whole statement, we call it as melting of ice. So what happened actually in a melting of ice, in case of ice, the composition or the main component is water. In case of liquid water, there also we have water. So in this case, initially it was water and finally it is also water. So here there is no formation of new substances. You try to know that one. In case of physical change, there is always no formation of new substances. And one more thing is, you can convert that liquid water into ice back, and what we call it as? We call it as freezing of water. And what we have to do for that? We are supposed to cool the liquid water, and so that you are going to get the ice back. So try to know, ice can be converted into water and water can be converted into ice. And now what I am going to say is, physical change is always reversible. So if we see these two conditions in any change, and that change we call it as physical change. I repeat, what are the two very important the terms involved in physical change? There is no formation of new substances and can be reversed by reversing the condition. Okay, so I am going to write the key terms involved here. So in case of a physical change, no formation of new substance, and it is always reversible in nature. If you reverse the condition, and you are going to get the original things back, and such kind of change we call it as a physical change. So now if you want to define the physical change, the change in which there is no formation of new substances and can be reversed by reversing the condition is called physical change. One example I gave you, that is nothing but a melting of ice. Some other examples we'll see, so that it will be clear what actually the meaning of physical change stands for. The first one is melting of ice. Okay, and if you heat the ice, you are going to get the water. Okay, and if you cool the water, you are going to get the ice. So one more I am going to write, that is evaporation of water. So just to see, evaporation of water. So now we'll see whether this example is for physical change or not. Evaporation of water, and what we call it as, if you take water and if you heat that, and water is going to be converted into water vapor, right? And here there is no formation of new substance. Water we have, and in water vapor also we have the water content. So that can be reversed. If you reverse the process, that is nothing but water vapor what we have, and if you cool that, you are going to get the liquid water back. So there is no formation of new substance and can be reversed here. Therefore evaporation of water is also an example for physical change. And one more I am going to consider, that is sublimation. Sublimation of iodine is also an example for physical change. So I hope you remember what actually the meaning of sublimation is. If the change in state of matter from a solid to directly gas without forming liquid, and that we call it as sublimation. One very simple example I will give you. If you consider camphor as an example, okay, and if you just heat that, the solid camphor is going to be converted to gaseous form, isn't it? So similarly, iodine is a solid substance, and if you heat that, solid iodine is going to be converted to vaporized form of iodine, okay, and iodine is the same substance, there is no formation of new substance. And if you just condense or if you just cool that iodine vapors, we are going to get the iodine solid back. That is nothing but gas to solid you are going to get, and that is also called sublimation. Therefore, sublimation of iodine is also an example for physical change. So now the final conclusion is there should be no formation of new substance, and the process should be reversible by reversing the condition only. So for one, if you just heat that, and for the other process we have to cool that, reversing the condition, and that kind of change what we observe, and that we call it as physical change. Now I am going to move with the second one, that is chemical change. So we'll see what actually the meaning of chemical change stands for, and it is exactly opposite, and one can guess there is a formation of new substance. There is formation of new substance, and remember, chemical change is irreversible in nature. So if you reverse the conditions, you are not going to get the original things back. That we call it as reversible in nature. So a change in which there is a formation of new substances and cannot be reversed by reversing the condition, or I can say irreversible in nature, and that kind of change we call it as chemical change. We'll see the example and you will come to know that one. One very simple example I am going to consider. So curdling of milk. So curdling of milk, what happens actually here? Milk is going to be converted into curd by the action of some bacteria. So milk is going to be converted into curd. Okay, so milk is one substance and curd is one substance. There is a formation of new substances here, and you cannot get back the milk from the curd, isn't it? So that process is irreversible. So a change in which there is a formation of new substances and that is irreversible, and that kind of change we call it as chemical change. So some examples I am going to write here. So one is curdling of milk. Curdling of milk. Second one I am going to consider digestion of food. You just see here, digestion of food. The food particle is going to be converted into simpler substances to give energy. Okay, and of course there is a formation of new substance, and digestion is, you cannot reverse that, isn't it? So therefore formation of new substance we are going to see, and you cannot reverse that one. Therefore digestion of food belongs to a change, we call it as chemical change. Cooking of food you can consider. Cooking of food, of course one can guess that is an example for chemical change. Rusting of iron articles. Rusting of iron. When iron metal or iron article is exposed to atmosphere in the presence of moist air, there is a formation of a brown colored layer on the surface of iron, that we call it as rusting. Okay, and there is a formation of new substance, that substance is brown color layer, and you cannot reverse that also. Therefore rusting of iron is also an example for chemical change. Similarly, we can give n number of examples for physical change and chemical change. And one example I am going to consider, and you should guess whether is an example for physical or chemical. Fermentation. Fermentation is nothing but a decaying of a substance, and now you just imagine whether the fermentation is physical or chemical. And I told you already, if you want to guess whether it is physical or chemical, apply the condition. Okay, and if there is no formation of new substance and reversible, that is a class we call it as physical. If there is a formation of new substance and you cannot reverse that one, that is a class we call it as a chemical. In fermentation process, the substance or the particular food is going to be decaying. Okay, some new substance is formed and you cannot get the reverse back. So based on these two conditions, now I can say fermentation or decaying substance, decaying procedure, we call it as a chemical change. So that is all about the first concept, what actually the meaning of physical change and what actually the meaning of chemical change, and these two are the changes around us. And now we are going to concentrate only on the chemical change. Okay, so see, this is the process or the observation what we observed. Okay, so this chemical change what we observed, and that can be written in the form of reaction. Okay, and that writing the chemical change in the form of reaction, and back we call it as chemical reaction, and the respective equation we call it as chemical equation. So now what I am going to say is chemical change can be represented in the form of chemical equation. Okay, I repeat, chemical change can be represented in the form of chemical equation. So now we'll see what actually the chemical equation stands for. So now I am going to talk about the chemical equation and the reaction involved. Practically we know it as the chemical reaction. Okay, so remember, chemical equation means there should be always chemical change only. For physical change, we write only a kind of a reaction, just a statement or simple words we write. But in case of chemical change, we are going to write in the form of an equation here, and that we call it as a chemical equation. Okay, so try to know chemical change is represented by chemical equation. Okay, and now we'll see what actually the chemical equation stands for and what are the terms involved, and later we'll see some examples for that. So now in general I am going to consider we have one substance A, okay, and that is going to combine, or that is going to react with B, okay, and you are going to get a new compound C. In general, this is not a particular any reaction, in general I have written. So what I am going to say here is A is one substance that reacts with one more substance B, and you are going to get a new product or a new substance that we call it as C. And I told you already, in a chemical change there is a formation of new substances here, and anyhow I can represent here C is a new substance formed, and actually in some cases this reaction cannot be reversed. Let us assume for some particular example. So if we write any chemical change in this form, and that we call it as the chemical equation. Okay, and now this is the arrow mark we have, and the left part of arrow mark we call it as reactants. You try to know this, we call it as reactants, and the right part of the arrow mark we call it as a product. Okay, so reactants and the products we have. So it is very easy to identify which one is reactant and which one is a product. Okay, the left side part we call it as reactant, and the right side part we call it as a product. Okay, and now we'll see what actually reactant stands for. I told you already, there is a chemical change involved. In case of chemical change, let us assume these two are the species or a substance that has to react, that has to combine, isn't it? So the species which reacts or which combines or which unites, you can say, and that we call it as reactants here. And after combination or reacting, the new product what we get in the reaction, and that we call it as product. That is the actual meaning of reactant and product. And now you ask, what is this kind of arrow mark stands for? This arrow mark with a pointing towards the right hand side stands for from A and B you are going to get C. This is how we are supposed to show like this. Okay, so from A and B you are going to get C, and this is how we write the chemical equation. Okay, and sometimes in some chemical reactions we have to mention the pressure involved, the temperature involved, whether the gas is released or not, whether the solid formation takes place or not. We have n number of representations for that. Okay, so usually if we mention this kind of a symbol, that is delta you can say, and that indicates the process, we call it as heating. Okay, you try to know about that. And if we use a kind of a symbol, that is arrow mark pointing upwards, arrow mark pointing upwards, and that shows that there will be liberation of gas. liberation of gas, evolution of gas. And if I show the arrow mark pointing downwards, and that we call it as a precipitation. That I call it as a precipitation. Precipitation is nothing but formation of a solid. Okay, there is a formation of solid, and sometimes we represent H nu. Okay, and that is nothing but light, or in presence of sunlight we call it as H nu. H is a Planck's constant and nu is frequency of radiation. So similarly, these kind of some symbols we used in a chemical equation to represent what happened actually in the chemical equation. Okay, heating, cooling, and sometimes gas is liberated, and formation of solid we call it as precipitation, and these are the some symbolic terms what we are going to use. Okay, so now this is the fundamental concept of writing the chemical equation. Okay, and now we'll see one particular example by conducting the experiment. Okay, and how we are going to convert the chemical change in the form of a chemical equation. So let me consider one simple experiment and simple activity you can say, and here I am going to represent it by representation. Okay, so you need to imagine what I am going to say. So let us assume I have this is the heating instrument used in lab, and we call it as a Bunsen burner. Okay, and of course we have a flame. Okay, and here I am going to consider one magnesium rubber. Okay, and here this is I am supposed to hold this using the pair of tongs, I can call it as. Okay, and of course we are going to see a kind of flame. Okay, and this I call it as magnesium ribbon. This is magnesium ribbon, and this is a Bunsen burner and a pair of tongue. Usually in this the chemical change we are going to get a kind of a powder, and I am going to collect that powder in a watch glass. Okay, and this powder what I am going to get, that will be magnesium oxide. Magnesium oxide. This is one simple experiment, and that is nothing but the one chemical change what we are going to observe. Okay, so let me explain that one what we have. So I have magnesium ribbon, a solid very thin ribbon kind of structure, that is a magnesium element, and that I have to burn. I am going to burn that one. So for that burning purpose I am going to use that Bunsen burner. I just kept in a slant manner so that I am going to get the magnesium oxide powder in a very easy manner, and here I am going to place a watch glass so that I am going to get the magnesium oxide. Okay, so what happened in this particular experiment here? So magnesium ribbon is going to burn, and we know that one burning is nothing but combustion. Okay, and combustion is nothing but oxidation. Okay, oxidation, combustion, burning, altogether the same thing, and oxidation is nothing but addition of oxygen to a substance. We call it as oxidation. So after burning the magnesium ribbon, and we are going to get the new compound, we are going to get a new substance, and what is that new substance? Magnesium oxide. So in this experiment there is a formation of a new substance, that is a magnesium oxide, and you cannot reverse that. Therefore this change what we are observing, and that is an example for chemical change. And now I told you already, chemical change can be represented in the form of chemical equation. So now we learn how to write this chemical change in the form of equation. Okay, so what is the original species or substance what we have? So magnesium. So magnesium I am going to write here Mg. Okay, and I hope you remember elements are represented by symbols. I repeat, elements are represented by symbols, whereas molecules are represented by formula. So magnesium is element, therefore we have a symbol for that, that is a Mg is a symbol for magnesium. So what happened? Magnesium has oxidation or burning or reacted with oxygen. Okay, so O2 I am going to write here, and now O2 I have written. I have not written actually O. So try to know the difference between O and O2. O is oxygen atom, whereas O2 is oxygen molecule. Okay, atom and molecule. Try to know atom and molecules are the constituent particles present in matter. And we know that matter is anything that has mass and occupies space. So matter consists of atoms or molecules, and try to know atom cannot exist independently in nature. If we have oxygen, that is O, O cannot exist independently. Okay, that has to combine with one more O, and you are going to get O2, that we call it as oxygen molecule. Atom is highly unstable, and that is going to try to be stable, and we are going to get a molecule. Therefore oxygen, we write O2 stands for oxygen molecule here. So magnesium reacts with the oxygen molecule, and the aroma, that is nothing but the new compound is going to be formed. And what is it actually? That will be magnesium oxide. Okay, magnesium oxide is a compound, therefore we are supposed to use the formula, particularly molecular formula, and the formula will be MgO, and MgO stands for magnesium oxide. And here Mg valency will be 2 plus, and O valency will be 2 minus. Okay, and here I use the concept called valency. Okay, so try to know valency is nothing but the combining capacity of an element. We call it as valency. And in one more way also we can define, that is number of electrons present in outermost orbit of an atom. We call it as valency. Okay, so magnesium valence is 2 plus and the oxygen valence is 2 minus. One is cation and one is anion. Positively charged ions we call it as cations, negatively charged ions we call it as anion, and together we call it as magnesium oxide. So magnesium reacts with oxygen, or magnesium is going to burn, or magnesium undergoes a combustion, or there is oxidation of magnesium, you can say like that, and we are going to get the product that we call it as MgO, and that is the new product that is formed. So this is one example what I have given, how chemical change can be represented in the form of chemical equation. We'll see one more example of the kind. The second example what I am going to consider here is, so I am going to consider conical flask. Okay, so this is actually the apparatus of conical flask, and inside the conical flask I am going to consider zinc granules. Zinc granules means zinc is element, solid state, and small pieces of zinc I am going to consider, and the top of the conical flask I am going to fix a rubber cork, and inside that I am going to introduce a glass funnel or a glass tube. Okay, and so that we can add something into the conical flask, and here I am going to pour a liquid that I call it as dilute sulfuric acid. I am going to pour dilute sulfuric acid. So here actually what happens, I am going to say, zinc granules we have taken in conical flask and we are going to pour dilute sulfuric acid, and after pouring dilute sulfuric acid there is a reaction between zinc and dilute sulfuric acid, and of course there is a release of a gas, and the name of the gas is hydrogen in this case. Hydrogen. That is one simple experimental fact what I am going to consider, and now we'll see how we can write this chemical change in a form of chemical equation. Okay, so try to know zinc is solid substance I have in the conical flask, and I am going to pour dilute sulfuric acid. Dilute sulfuric acid is well-known acid, and I have used the word called dilute because the amount of acid is less whereas the amount of water will be more, and therefore I use the word called dilute, and the gas released here is hydrogen. That is a chemical change. New compound is going to be formed, and now I will tell you how I am going to write this chemical change in a form of equation. We'll check out that. So we have a zinc. Okay, zinc is element represented by symbol Zn, And what I am going to add? I am going to add a dilute sulfuric acid. I hope you know sulfuric acid formula H2SO4, dilute sulfuric acid. Or you can mention DIL dot, that indicates a dilute, or if you don't mention anything, that indicates that will be dilute acid itself. So these two are going to combine, these two are going to react here. Okay, and what are the new products we are going to get? And one we know that very well, that is hydrogen gas is going to be eliminated. So the product what we are going to get is ZnSO4, stands for zinc sulfate. Zinc valency 2 plus, SO4 valency 2 minus. You are going to get a zinc sulfate, and the gas released is, that will be hydrogen. I told you hydrogen H2 molecular form, which is quite stable, we don't write in atomic form, and hydrogen gas is released, and I told you already, I am going to show the arrow mark pointing upwards, which indicates that there is a release or evolution or liberation of gas I am going to indicate. So the same chemical change I have represented in the form of a chemical equation here. Okay, and one more concept I am going to discuss here. The hydrogen gas what we are going to get, that is colorless and odorless in nature. Colorless, odorless, no particular smell we have for that. Okay, therefore hydrogen gas can be identified by bringing the burning candle or burning matchstick near the hydrogen gas, so that you are going to get a characteristic sound that we call it as a pop sound, POP, pop sound. From that we are going to identify what actually which kind of gas is going to be released. So this is one more simple thing how I can explain that chemical change can be written in the form of chemical equation. One more we'll see. Let us assume I am going to consider one test tube, and inside the test tube I am going to place lead nitrate. Lead nitrate I am going to place, which is colorless liquid actually, lead nitrate, and I am going to pour potassium iodide. Potassium iodide I am going to pour. So when there is a reaction of these two, there is a formation of new substance inside the test tube, and it has a characteristic property of that. Okay, so that is also a chemical change. We'll see how we can write in the form of reaction. Lead nitrate, the formula we are going to write. So lead nitrate, PbNO3 twice. Pb stands for lead, NO3 minus nitrate. Pb, the valence will be 2 plus, therefore PbNO3 twice, lead nitrate. That reacts with the potassium iodide. I hope you can guess the formula. Ki stands for potassium iodide, and what we are going to get here, and the main product what we are going to get here is, let me write here, that will be PbI2, and one more product I am going to get, that will be KNO3. Lead iodide and potassium nitrate we are going to get, and this lead iodide, that will be you are going to get in the form of precipitation, formation of solid, and try to know it has a characteristic color, that is a yellow color in nature. So actually these two both are colorless liquid only, and after mixing that we are going to get PbI2, we got a characteristic property, that is a color. So some chemical change can be represented in the form of color, so that we can understand the chemical change has been occurred in this particular example. So this is all about how we can write the chemical change in a form of a chemical equation. And try to know, in case of chemical change, sometimes there is a change in state of matter, and sometimes there is the characteristic odor property, we get a characteristic smell. In some cases we get the change in color, as we have seen in this case, and in some cases sometimes temperature is decreased, sometimes temperature is increased. So all these are the characteristic property of chemical change in state, change in odor, change in color, change in temperature. All these are the characteristic properties of a chemical change. After knowing the concept that chemical change can be written in the form of chemical equation, and now one very important law we are going to learn that involved in a chemical change or chemical equation, and the name of the law is law of conservation of mass. So we'll see that now. Law of conservation of mass. So before moving with the actual statement, I am going to consider one simple example and we'll see what actually the law of conservation of mass stands for. I will consider one chemical equation caused by a chemical change, and that we call it as the formation of carbon dioxide. Carbon reacts with oxygen or burning of carbon, and we are going to get a gas, we call it as carbon dioxide. And here now we'll calculate what about the mass of the reactants and what about the mass of the product. So carbon, the atomic number of carbon is 6, whereas the atomic mass will be 12. For the carbon, the atomic mass will be 12. I am going to calculate the weight, therefore atomic mass you are supposed to consider. Oxygen, the atomic number is 8 and the atomic mass will be 16, and we have 2 oxygen, therefore I need to multiply it by 2. Okay, and if you simplify that or if you calculate that, and we are going to get the total mass as 44. Okay, if we add these masses, okay, 44 we are going to get, and we'll calculate in the form of product what we are going to get here. Carbon is 12 plus oxygen is 16. How many we have? We have the 12. Therefore simplified from 12 plus 32, and if we add these two, we are going to get 44 only. So in case of reactants, the total mass is 44 AMU, atomic mass unit, or grams you can consider, and here also we have 44. So before reaction and after reaction, the mass is the same. Even though it is a chemical change, before and after the mass will be the same. Okay, so what does the law of conservation of mass says? That mass can neither be created nor be destroyed. You cannot create, or there is no addition of mass, or there is no loss of mass, whereas the mass remains as it is, and that we call it as what actually the law of conservation of mass. And this law is going to be suitable for all kind of chemical reactions here. And since this law is going to be applicable, that's why we have to balance the chemical reactions. Okay, and now we'll see what actually the meaning of balancing the chemical reaction. So we'll see what actually the meaning of balanced chemical reaction. Okay, and later we'll see what happens if it is not balanced. We are going to see. So now I am going to consider what is the meaning of balanced chemical reaction. Balanced chemical reaction. So what is the meaning of this term I am going to consider? So we'll consider one very simple example. Okay, and the example is, I use the same thing. Okay, that is the same example, C plus O2, and we call it as CO2. That is the chemical change. So now what actually the meaning of a balanced chemical equation means? You have to calculate the number of atoms of an element in a reactant side as well as the product side. If they are same, and that equation we call it as balanced equation. And if it is not same, then we have to balance that. First, let me check out whether this reaction is balanced or not, and how to calculate that. Okay, we'll see one by one. So now we'll see what are the elements involved in that one. In this case, we have 2 atoms of an element, one is carbon and one is oxygen. So we'll see in case of reactants, okay, and how many atoms of an element we have. In case of product, how many atoms of an element we have. So I told you already, in a balanced chemical equation, number of atoms of each and every element should be same in case of number of atoms of an element in case of product also. So now we'll see what about the carbon. The number of atoms of an element of carbon in a reactants is 1. We have 1 carbon. What about the product? We have 1 carbon. So I am going to say carbon is balanced already. What about the oxygen? Oxygen we have 2. And what about this oxygen? We have 2 here. So number of carbon is the same in case of reactants as well as product. In particular, the number of atoms of carbon and number of atoms of oxygen, they are same in case of reactants as well as products. Therefore, that we call it as balanced chemical equation. And if it is not same, okay, let us assume here we have 2 and here we have 4, and that we have to balance the chemical reaction, and I told you already why we have to balance the chemical reaction: to obey the law that we call it as law of conservation of mass. One more example I am going to consider, and that I discussed already. When zinc reacts with dilute H2SO4, when zinc reacts with the dilute H2SO4, I hope we can guess the products. One will be ZnSO4 and one more will be, there is a liberation of gas called hydrogen. And now we'll see whether it is balanced or not. So for that I am going to consider the all elements of this reaction. So here the one is zinc, okay, and we have hydrogen, we have sulfur, and we have oxygen. The elements I have written. We'll see in case of reactants what is the condition. Reactants, and we'll see in case of products how many atoms of an element we have. So now we'll look into zinc. So in the reactant side, the left part of the arrow mark, zinc, how many zinc we have? We have only one. Okay, in the product, the right part of arrow mark, we have zinc, that is only one. Zinc is said to be balanced. We'll see about the next element, hydrogen. How many hydrogens are there? We have 2 hydrogens. In case of product also we have 2 hydrogens. Hydrogen, there is no big deal in that one. Sulfur, we have 1 sulfur in the left hand side. In the right hand side also we have 1 sulfur. Similarly, 4 oxygens we have in the left hand side and 4 oxygens we have in the right hand side. The number of atoms of each element in reactants and products, they are same. Therefore this reaction is also balanced chemical equation, and that has already obeyed the law of conservation of mass. And then question arises, if it is not balanced, what we have to do? We have to balance that chemical equation by following some simple steps. So what are those steps? How to balance the chemical reactions? We are going to discuss in the next session.